So given this situation, when we talk about topological quantum matter, it's important to notice that there are a few organizing principles that help us to discriminate between different types of topological matter. And actually, this will be Blackboard. You don't have to copy. I will distribute PDF in some ways. If you can read my handwriting, you're good. Yeah, that's a challenge. So, topological matter. I mean, if we talk about it, we have to make a few decisions. And, yeah, that's better. So first of all, there is one axis symbolically representing the strength of interparticle interactions. So we have to decide whether we want to talk about something that is strongly interacting. Can you read this? Yeah. In the sense that we have strong interaction-generated entanglement and so on, or whether we are operating in a sector where interactions are relatively modest, such that we have a chance to get away with some effectively non-interacting Landau quasi-particle-ish theories, right? Then there is another dimension where we have to decide whether we actually want to talk about gapless quantum matter where we have soft excitations, gapless. And at this point, this tends to be the more complicated part of the axis, as opposed to effectively inert or insulating quantum matter where we have excitation gaps present. Yeah? And finally, we have to tell whether our matter which we're interested in is fundamentally bosonic in the sense that it builds on bosonic fundamental quantum particles on the basic level, or fermionic. Yeah. All right, so that's the kind of decisions we have to make, and what I would like to cover in some sense in this talk is this relatively modest octant sitting down here, weakly interacting fermionic gap quantum matter, which is in a sense the simplest of all. I mean, the other 7 are a bit less understood at this point, but nevertheless it's important, and in particular it accommodates the physics of topological insulators and superconductors, which is of some importance to this school. Now, having been so modest, I mean, we can also say that what we are going to discuss tolerates, to a fair extent, reasonably strong interactions, and we can also go a bit in the gapless direction. I mean, bi-semi-metal is a keyword we have heard, but basically we will operate here. But within this framework here, within this sector, I want to be really general and not make too many specializing assumptions, etc. Yeah?
What about disorder?
So this is very disordered. Disorder is I love disorder. So disorder is, we will definitely tolerate disorder. And thank you. I mean, basically, always interrupt me. I try to be ultra clear. If I fail, immediately interrupt. Yeah?
Another question. For a theory where it's analytically limited price, does it make a difference whether you use a bosonic or quantum theory?
Yeah. To some extent, you have a Fermi surface, no?
Yeah.
I mean, in what I want, I like some Fermi surfaces in what. But we can. You have a point. I mean, not really. No. Okay. Fair enough. Yeah. Mm-hmm. All right. So. Given this setting, let's now consider a system. I was too pretentious. I'm not that tall. Okay. So what I would like to focus on now is actually topology ultimately, but we will see topology is strongly linked to symmetry. I mean, these two are twin brothers in this context. So symmetry and topology of this sector here. And to this end, let's consider the following setting. So this is now symbolically the type of systems we want to consider. Imagine a generally finite size system, your favorite piece of topological insulator, whatever. And before we get going and discuss what symmetry and topology mean for such systems, it is it is well to introduce a number of length scales and correspondingly energy scales, which will then organize our discussion later on. Yeah? So length scales, there is a macroscopic scale which is set by the extension of the system we look at. And then there is the ultimate extreme. Say we have some, or actually it's even smaller. We can zoom in here on deep microscopic scales, and then we will notice that there are some quantum particles moving here, and they have typically a de Broglie wavelength lambda that sets the ultraviolet scale in the game. And then we will also tolerate, here it comes, that there is some junk in the system. So there can be some kind of scattering going on, and that can be characterized loosely by some elastic mean-free path, which sets the length scale associated to some imperfections. Yeah? So these are roughly the length scales we have. And then again, I mean, we assume that our quantum particles here are, in a sense, weakly interacting, but we tolerate translational invariance breaking. So this is our system. And now, now I need, perhaps I can do this here. Now, in a very schematic way, I want now to, yeah?
So this lambda, is it related to the gap of the Hamiltonian?
No. It's, what I mean by that is the de Broglie wavelengths corresponding to a fictitious particle moving at the Fermi surface. So I haven't yet talked about a gap, but you're absolutely right. The gap is an important energy scale in gap quantum matter, which we have to consider. Definitely. I wanted to just make, it's just our ultraviolet scale. Okay. Right. So we can now, I mean, very schematically, introduce here an axis where we order our length scales according to size, lambda L, and here there will be the system size, and correspondingly, relatedly, we have energy scales which are associated to these. So the energy scale corresponding to lambda is sort of the Fermi energy. Here we have something like the inverse of a scattering time corresponding to a mean-free path. And here it gets more interesting. The energy scale relating to the actual system size depends now on whether you're dealing with a clean case, in which case this is irrelevant, or whether you're dealing with a translational invariance breaking system, which is strongly disordered. And in the clean case, the natural energy scale corresponding to the system size is Fermi velocity over system size. That is the ballistic time of flight a quantum quasiparticle will take a quasiparticle at the Fermi surface to rush one through. Yeah, that, I mean, the inverse of that sets an energy scale, which is the energy scale a particle needs to actually find out to discover that it's living in a finite size system. And in the disordered case, which I also want to cover, this will be the diffusion constant, which is material constant relating to the amount of dirt we have, divided by L squared. That is the inverse of the time a particle in a disordered medium needs to diffuse around and ultimately discover, hey, I'm confined in a finite size system. Yeah. Is that clear? I mean, so this is like an energy scale according to Heisenberg principle associated to that time scale. Yep.
Can you repeat what D is?
D is the diffusion constant. Yeah. If you look into the notes, which this is actually written. Right now I'm just saying it, but don't have. Okay. So why I'm bringing this up, because depending on where we are and what kind of phenomena we are interested in, whether we're interested in ultraviolet physics or ultra low energy physics, different physical principles matter. Yeah. And very roughly, we can say that up to, say, here, we really have to worry if we want to know something, understand something on an atomistic level, ultraviolet physics, band structure stuff. We should be worried about microscopic details. I mean, we really have to look into basic microscopic structures. Yep. Just symbolically, nothing. It's just, here I will draw now a number of things you have to consider if you are interested in this. And all I want to say here, there is no axis, is that if you want to do physics here, then you better address microscopic stuff. Clear, right? Beginning as of somewhere here, the dimensionality of your system begins to play a role. This is dimensionality. Now, what do I mean by that? All systems are ultimately three-dimensional, yeah? But if you look at something like, say, a semiconductor heterostructure or something which is very flat and very wide, yeah? Then at some point, excitations in transverse direction will be frozen out, and the system will behave effectively two-dimensional, yeah? And this doesn't happen down here, but it happens at some moderate energy scale. So this is where dimensionality kicks in, and we have to discriminate between effectively one-dimensional, two-dimensional, three-dimensional, and if you are theoreticians, you can go to eight-dimensional, whatever. Now, about at a slightly larger scale, very vague, yeah? Here, fundamental symmetries will begin to play a role, and I will spend a great deal of time on explaining what I mean by symmetry. So wait a second, if you want, I owe you an explanation of what's going on here. And finally, at the largest scales, I mean, we heard that this morning. I mean, if you really explore the system as a whole and you are sensitive to its global structure, including its topological nature, then you should also think about topology. And it's an important disclaimer. Yeah? You could also say, I have some skyrmion material. We have some topological defects around or some vortex matter. This is not the type of topology I want to address in these talks, but it's rather the topology of the system at large, in a sense. Okay, so that is basically very roughly the setting. And I will now spend quite some time on introducing and discussing symmetries as a really important organizing principle for all that follows, and then we will draw the connection to topology. And actually, I thought I have 3 times 90 minutes, but I learned I have only 3 times 60 minutes, and it doesn't matter. I can stop any time after a certain cutoff which I want to reach, and I will reach, yeah? So, but, I mean, these two I definitely want to introduce. And now I need more space. Okay. So, let's start discussing symmetries. You can forget all I said so far. Symmetries in quantum mechanics in the most general terms. So, symmetries. The beginning of this will be known to pretty much everybody. I just introduced it to introduce some notation, but then it may get a little bit less familiar. So what do we need to fix a symmetry? We need a certain amount of data, yeah? I mean, first of all, to talk about symmetries in quantum mechanics, we better have a Hilbert space. And I call my Hilbert space H, and for convenience, I will assume it to be finite dimensional. It doesn't matter much. In my Hilbert space, I have states, psi, which I also need. We then need a symmetry group. Group. And on an abstract level, this is a group G, where it can be abstract, and in this group live abstract elements small g. And we will make them then more concrete when we discuss how they act on states psi. And finally, if we actually want to discriminate, I mean, is the system symmetric, yes or no, then we need to talk about its Hamiltonian. I mean, how it behaves on so we also need a Hamiltonian. 8. Okay. Now, these abstract guys are now represented in concrete terms via their action on states. Yeah, and that's what we also need. So the symmetry group, or I can call it G, is represented by a linear representation on H through transformation. Psi maps to, for example, our abstract group could be Z2, right? 2 elements, plus and minus 1, binary group, and this could be a space reflection. I mean, a representation of this group where it acts by reflection or doesn't act at all, something like that. And it now turns out that many symmetries in quantum mechanics are unitary in the sense that this map, which I associate to an element of G, is a unitary map in the sense of quantum mechanics in Hilbert space. Yeah? And these such unitaries include, I mean, say, translations, rotations, crystal point groups, and several others more. Now, a few years ago, 2010-ish or so, I would have claimed these unitary symmetries, when it comes to topology, don't matter too much. You can essentially forget about them. But since 2010 and 11, there has been the advent of crystalline topological quantum matter, and we will hear a lot more about that later on. So I'm rather more modest now, and I mean, unitary symmetries are definitely of importance for our story here. Not so much the story I want to tell you, but certainly about what Titus has to say later on, and others. But at any rate, they have to be seen in connection to their twin partners, the anti-unitaries. So there exist also anti-unitary symmetries. Others are anti-unitary. Now let me just remind you what an anti-unitary map is. Before doing that, just notation. In the context of these lectures, when we talk about anti-unitary symmetries, I will represent them always by the symbol theta. It's just notation, yeah? My anti-unitaries are always called theta, and I describe to you later how they act. Just a reminder, what is an anti-unitary? Or do you all know anti-unitary? Should I repeat? Yeah, I see some people nodding. Okay, a map, theta acting in a Hilbert space, like this one, is anti-unitary. If the following holds. We have a few conditions. See, it's all about unitarity in a sense. So remember how you fix the unitary operation. You take an Hilbert space state, act on it with some transformation, and then take the scalar product overlap with another state, same transformation acting. And if it was unitary, they would cancel out, and this would be equal to the original scalar product. And an anti-unitary does almost that, except that there is a complex conjugation. Yeah, that's the definition. And this is then by virtue of the definition of the complex scalar product equal to the scalar product in reverse order. So that's an anti-unitary. There is a second criterion, which is, or actually it's implied by this, but an anti-unitary, an anti-unitary, but is a consequence of this, if it acts on a state multiplied by a complex number, you can pull out the complex number, but you have to pay with the complex conjugate for that. So you have this. And Z is complex. Another important point, you can always think of an anti-unitary as complex conjugation times something unitary. It's also important. So there exists a unitary map, and we are in an n-dimensional space here, so it's an UN transformation with the property that the anti-unitary is the unitary times k, and k is my symbol for complex conjugation. So it's just complex conjugates, nothing more. That is all math. Now comes one important point from physics. And that's an axiom, actually. It means essentially what I'm using here, that twice time reversal acting on an operator reproduces the operator. And the consequence is that if I act twice with an physically meaningful anti-unitary, I get either the unit map or the negative of the unit map. That is, it's physics condition. And in practice, when we work actually with topological insulators and so on, often we have a situation where in the former case, where theta squares to unity, we can find a simple representation where theta is just complex conjugation, right? If you twice complex conjugate, you get unity. In the other case, it is often or usually possible to I times minus I to reduce theta to complex conjugation times a simple 2 by 2, which has a property that if you build the square of this, you can do it, you square to -1. These are just convenient representations. I'm just showing them because you see them very often in papers in practice. Now, examples of this include the usual suspects. Time reversal is anti-unitary. Particle hole charge conjugation. Etc. And if you are a bit at a loss as what I mean by that, that shows good taste, because I think there is only a few situations in physics where widespread and global notation is so confusing as in this business. Yeah? You can do the experiment. Maybe you have already observed it. Take a crowd of physicists and ask them little n of them, and ask them what they mean by particle hole symmetry. And chances are you get n different answers, and everybody is of course right. So there's ultra high level of confusion, and I myself tend to be very confused. And but I will want to share with you my current understanding of the situation, and maybe it helps a little bit to actually discriminate, say, between particle hole and charge conjugation and so on in concrete settings. But be aware, it's normal to be confused about this. Okay, so question up to this point? Yeah.
What are this condition theta squared equals plus
very good. What you require is that if you take a quantum mechanical operator and on an operator, this operator acts in an adjoint, so it acts like theta, theta, and if you apply twice, the operator should reproduce. That's the condition you impose. And if you then ask yourself, this still leaves you room. Theta can be squared to 1 or -1. And if you then dig a little bit further into the matter, then you realize that it's either plus or -1. These are the two options that are realized. Yeah? Yeah, very good. And the rule of thumb is that spin 1/2 systems have -1 and spin 1 have +1, but not always. Yeah. Okay. More questions, maybe? Okay. So now comes a very important point for our story here. see, when you talk about unitaries, it's clear that there is an infinite multitude of different unitary symmetries. You can, not infinite, but lots of them. You can discriminate. With the anti-unitaries, it's like there is only 10 different cases. 10 different symmetry classes in the sense that you give me your favorite quantum system. I identify its irreducible representations. I'll be telling a little more about what I mean by that, but really the sectors in which the Hamiltonian is fundamentally represented. And then I can put a sticker on each of these. And the sticker has labels in it. I mean, it goes from 1 to 10 in a certain notation which we introduce. And it identifies precisely the type of anti-unitary symmetries that are realized. Yeah? And that will be an important part of our story. And let me explain how it comes about. So there are 10 fundamental anti-unitary symmetry classes. And they are, in a way, they're important part, together with physical dimension, they are actually the essential part or part of the story that leads to classification of topological insulators and superconductors. Yeah. So there are 10 symmetry classes, anti-unitaries. And what I present to you now is a cheap and nutshell way of introducing them. So this is nutshell. But nutshell also means that it's not very physical. And in the second part of the story, I will then explain a little bit more how it really connects to real physics. But so far, we are a bit formal and simple. And we just define the following. A system is time reversal invariant. I switched to this way of writing. Is this a good idea? Let me just try. Invariant. If the following, that's the definition now. If there exists an anti-unitary, therefore theta, some anti-unitary symmetry, let's call it theta t, such that theta t stabilizes the Hamiltonian in this sense, yeah? And we call it, I mean, if we find an anti-unitary symmetry, no matter what, and it does this with the Hamiltonian, we call the system time reversal invariant. And we now have 3 possibilities. And that leads to a table, and yeah, that's actually very smart. I do my tables here. We can write down a little table listing the different options we have. Here are 3 possibilities. Yeah, there, really there. So jump from there to here. Yeah, here comes the table. We can ask ourselves, is a symmetry present, yes or no? And on top of that, if it is present, we can ask ourselves, are we dealing with a guy that squares to 1 or minus 1? These were the 2 options we have, yeah? And if the symmetry is not present, then we just don't care what it does. Yeah. And let me call this is the label, let me call this T0, no time reversal symmetry. If the symmetry is present and theta t squares to plus 1, I call this T1. That's one option. And if the symmetry is present and theta squares to minus 1, I call this T minus 1. And I can categorize all Hamiltonians according to one of these 3. So that was one step. Now, I just mentioned it. There is systems which have, this here, are usually spin 1/2 systems, but there are counterexamples to that. Do you want to see a counterexample? I just tell it. If you ask me if Dirac fermions, 2 dimensions, scalar potential. has the property that it you can come up with such an anti-unitary. It squares to -1, but there is just no spin inside. I mean, spin doesn't matter. Spinless particles. It's so be aware. In textbooks, you find this at always theta squared -1 is spin 1/2. It's not always the case. Good. So that was it. Then comes another definition. A system is charge conjugation symmetric. Or invariant. If we can find an anti-unitary, theta C,